Common to see on chemistry standardized tests like the AP exam, like the SAT subject exam, which, by the way, makes me think, I'm going to jump off on a tangent. I get a lot of people this time of year asking me about the SAT subject test for chemistry. And people are asking my opinion on whether they should take it in May or in June. And from my experience, I strongly recommend that you sign up and take it in May. And I know that there's a lot going on in May, but you're already going to be studying chemistry for the AP exam. Our final exam in here is coming up pretty soon. It's May 4th. It's the Friday before the AP exam, which is on the next Monday. So we do that to just, because you have to be studying for the exam anyway, we want you to try to put everything together, and we'll give you the final exam on that day. Which means on the exam day, we'll have something else to do. We'll do a lab. Our final exam in here is May 4th. Thank you.
He knew it was coming.
I knew it was coming. Take the SAT subject test. If you're going to take it in chemistry, take it in May. Because I think that it's that Saturday before the AP exam. If I remember right, it's the first Saturday in May usually. And you'll already have everything fresh in your mind, and why not just take another exam at that time? The offering in June requires you, after you've had a break from the very intense studying chemistry, you have like 3 weeks off, then you got to pick up chemistry books and start studying again. You will not want to study any chemistry, I guarantee. Even if you like it, you'll just be worn out. So every year I have people in June say, yep, should have taken it in May. Yeah?
You know when the deadline for signing up for SAT?
I have no idea. No. I've had a few people talking about it so far, so I think people are signing up, but I don't know when the deadline is. The counseling I don't know. You ask the counseling office. I was going to say their website, and I think they keep their website up, but I don't know if they answer all the questions like that.
It's on the college board.
Is it? I will say that the SAT subject test would be easier than the AP exam. It's short. You only have an hour to do it. There's 60 questions. There's one format on the SAT test that's different that we won't do at all. It's a true-false section. It's like a cause-effect kind of thing. But it's the same topics, just in a different format of question. Anybody have anything about that? All right. So anyway, that was a tangent. I want to come back to this now. If we look at how many electrons can go into different energy sublevels and overall energy levels. In the first energy level, there's 1s. That's it. There's room for 2 electrons, and then it's full. It's done. Second energy level has 2s and 2p. You see, as we go bigger and farther out from the nucleus, there's more sublevels, and they can be more complex. So this gives us how many total electrons are possible. 3s holds 2 electrons, 3p holds 8, and 3d holds 10. I'm doing the addition for you, Nathan, so you don't have to. And add that all together, and you get 18. And then in the fourth energy level, 4s, 4p, 4d, 4f, you'll notice that every time you go up by 1 sublevel, that adds 4 electrons to it. So there's a total of 32 electrons. So this formula right here, you may see again, it's good to know it. If you know n, the energy level, 2n squared would be the number of electrons possible in that energy level. What would n squared give you? N squared would be the number of what in an energy level? The number of orbitals is right. Yeah. In n equals 5, I even included this thing. 5G is not bogus. It is possible to have a sublevel that's 5G. It would just take a lot of electrons to have an electron in the ground state of 5G. And it's possible that electrons could excite to a 5G level. What's the matter? You want to leave my class? Everybody's taking off on me. Go ahead. Go on. I give you shamrocks. It doesn't mean anything to you.
Oh, it wasn't even funny. I was on his friend.
Go, please.
Bye.
Not coming back.
You don't have to ask permission to leave, and please don't say goodbye when you do. Okay. All right, so take a look at this. This should be easy. I think we talked about this yesterday. for nitrogen, 7 electrons. Which is the correct representation of the 7 electrons in nitrogen? Here's a hint. It's not D, because D has 8 electrons in it. It would be too many. So which one is correct for nitrogen?
Oh my god.
Jane signaled the answer and she was right. The rest of you have an idea? No?
What?
Okay, let me see it on your hands. It's for Johnny and Nathan. Yeah, that's good. That's right. Yeah, that's good. Uh-huh.
What are you doing? That's what I did.
I'll wait for you, Carol. There it is. Yeah, you got it.
Illuminati.
Yeah.
That was an answer.
How is this a... I did this.
Right? Alright.
Oh, I see it now.
That's right. It is A. The I don't know sign language, so you would have gotten me on that one.
Yeah, and you know what sign language is?
What sign language is?
And sign language what A is.
Oh, I think somebody had like this, right? A? Okay, well, there it is.
Yeah, so E. Right, man?
Why is A the correct answer on this one? Why not B? B looks like it's pretty good because in 1S we put an up arrow and a down arrow. Then it was full. We went to 2S. Up, down. It's full. We go to 3S. 3S. 2P. Up, down, and then up. That's 3 more electrons than 2P. What's the matter with B? Yeah? Exactly. That is because of what we call Hund's rule. And I'm going to have a nice big improvement. I never thought about this, but in 5th hour asking, what nation or what country was Hund from? We all just call it Hund's rule. Yeah, was he like Attila the Hun? Was he a scientist too? No, different guy. This is Friedrich Hun, and next year I'll have a picture of him. If you look up a picture of him, he's a clone of Schrodinger. It's great, same glasses.
Where's he from?
Where do you think?
Germany.
Friedrich? Oh yeah, he's from Germany. Yeah. Man, all these quantum guys, German. Hun.
Oh man.
Right. Yeah.
Man.
You thinking Schrodinger on that one?
Yeah.
Yeah.
What's some modern?
Okay, well anyway, enough of Hund. What does this rule say? He says that when you have that term comes up again, degenerate orbitals. I use that word not because I'm in love with it, I'm not. But your professors will love that word. In different subject areas, the word degenerate always comes up in college. You'll hear it all the time for different things. Degenerate means you have multiple things, same energy. Or you have things that are multiple things that you can't really distinguish between. So I'm just using that word to get you ready. When you're filling sublevels that have multiple orbitals, put one in each before you pair any up. So A was correct because of that, because of Hund's rule. Yes?
We can periodic table. How can we go right from 4s to only 3?
3D?
Yeah, why do we go 3 to 40?
Yeah, because the D sublevels, the 3D is in the 3rd energy level. Yet it's in the 4th row of the periodic table. The reason for that is because Ds are a sublevel that has high enough energy that it actually is higher than the next energy level's S. So when you get to Ds, they'll always be higher in energy than the next S. So in the 4th row, well, when in the 3rd row, you got 3S and 3P, and then you're done. The 3rd row ends with argon, and then you got to go to the next. Well, there's still 3D. Where does that go? Well, you have 4S at the beginning of the 4th row, but then is where we see the 3D come in. So Ds are high enough energy, they'll overlap into the next energy level. Every one of them does that. Hund's rule is an important one to remember because often you'll be asked about how many unpaired electrons does an atom have. Nitrogen, you'd have to write the arrangement correctly to recognize nitrogen has 3 unpaired electrons. And unpaired electrons are a pretty big deal. When we start to write dot structures, when we did dot structures back in the organic chapter, it was significant how many unpaired electrons an atom has. All the noble gases, they don't have any unpaired electrons. And there's something very special about them because they don't have any unpaired electrons. They're really stable like that. When you can finish an energy level, when atoms can finish an energy level and they have a full p with all of the p electrons paired up, that is especially stable. All right, now I want to have you take a look at this last thing here in the quantum theory, and that gets us to electron configuration. You've seen this before. This is a way of expressing where electrons are, how they're arranged in an atom. This is not as descriptive of writing the energy level diagram with the arrows on. With that up, down, and you can tell how many unpaired electrons things have with the energy level diagram. You can't necessarily from here. Was she there this time? Oh, good. So fluorine, atomic number is 9. We find it on the periodic table. So we have to account for where the 9 electrons are. The electrons always start close to the nucleus. 2 electrons in 1s, so we call that 1s2. Then it goes out to the next, 2s, it fills with 2. Then it goes out to the next, 2p. It only has 5 electrons out there. 2p has room for 6, but we don't need all 6 places. We only need 5, and then fluorine's out of electrons. When you read these off, please don't say 1s squared, 2s squared. I know that's what it looks like, but when we're in chemistry, we're not squaring anything. We just say 1s2, 2s2, 2p5. Okay? Can you look at this and determine how many unpaired electrons fluorine has? You have to understand that whole energy level diagram thing to be able to answer that. How many are there? 1 is right. Yep, it's 1. And just to make this clear, I'll use this as an example because it's short. 1s is full with 2 electrons. 2s is full with 2 electrons. No unpaired electrons there. But then 2p, it's got 5 electrons in 2p. There's the first 3, and then we come back and pair them up, 4 and 5. So that thing right there is an unpaired electron. That unpaired electron makes fluorine very unstable. It's got the highest reduction potential of anybody. Man, it wants badly to pair up that electron. You all right? You need a moment? Okay. I'll do this. With potassium, you can see that potassium has atomic number 19, and the bigger the atom gets. Now, fluorine was quaint. It was little. It only had 3 terms, 1s, 2s, and 2p. Potassium, getting bigger, is going to start getting longer. 1s2, 2s2, 2p6, 3s2, 3p6, and then 4s1. That accounts for all 19 electrons in potassium. Now, that's only 19. You can imagine how long they will get. What if we go out to 89, right? Well, they're obnoxious. It's terrible. So you know that we can shorten electron configurations. You remember this from Chem 1. What we do is we take advantage of the fact that energy levels really end where the noble gases are. I consider the noble gases like the anchors of the periodic table. When we go to the end of full P, that finishes an energy level. Even though I know that really when you get to 3P and fill that, there is still the 3D, isn't there? But the D's are kind of outcasts as electrons go. The S's and the P's are the cool ones. So that's what we really focus on. And so when you get to the end of a row, in this case, we finish the 3p, that's where argon is. And you can replace all those first 18 electrons and where they are by just writing argon symbol in brackets like that. That will shorten the electron configuration. You could say for potassium, the potassium electron configuration is just argon core 4s1. And when I say argon core, that just implies all 18 electrons up to 18. I didn't mean to say it like that. That includes the first 18 electrons. which finishes the third